Okay, this is AC Part 2, Review Lecture 8.2b. If you skip Part 1, please go back and do that before you come here. Okay, now I left some review slides in here, which I'm not going to go over because I did over another video. Okay, so power and alternating circuits. The instantaneous rate at which energy is dissipated in a resistor can be written as power of time equals I squared R, same as we had before. But now I is I sine omega dt minus phi. So it gets a little bit more complicated. So we have power equals I sine omega dt minus phi, that squared, times R. Now we can pull the I outside, and then we end up with power equals I squared R times the sine squared of omega dt minus phi. The heating effect produced by AC current with a maximum value of I is not the same as that of a DC current of the same value, because I is only there for a very short time. Maximum current only occurs just basically instantaneous as it reaches the peaks of the cycle. Now, over one complete cycle, the average value of sine theta, where theta is any variable, is 0. You can see that by just looking at this. But the average value of sine squared theta is 1/2. And you can see that by looking at this. This is the sine squared versus theta. This is sine versus theta. Power equals I squared R over 2. Now, we want to make that look like the DC power, which is I squared R. And we can do that by replacing I with I over the square root of 2. If you do that, then power equals I over the square root of 2 squared times R. And then it looks like I squared R, DC. Makes it easier. Now this term, I over the square root of 2, is called the root mean squared, or RMS value. It's sort of an average. So I RMS equals I over the square root of 2, and then power equals I RMS squared times R. Alternating voltages and EMFs can also be used in terms of RMS values. So VRMS is V over the square root of 2, and ERMS is E over the square root of 2, where I, V, and E are all amplitudes. In other words, peak. In a series RLC circuit, the average power P of the generator is equal to the production rate of thermal energy in the resistor. So P equals ERMS, IRMS times a factor called a cosine phi term. This is called a power factor. And this is related to the phase of the circuit. This looks a lot like P equals EI, or P equals VI. The only difference here is this term. So IRMS equals ERMS over Z. We want to make this look like I equals V over R. And we introduced C before. So Z is sort of going to stand in for R. That's the impedance. So power equals IRMS squared times R, or ERMS over Z times IRMS times R. That equals ERMS times IRMS times R over Z. It's hard to say really fast. The cosine of phi is a power factor. And what is this? If we compare that with the stuff on the previous page, we find out that the power factor is R over Z. Now, RMS values are used when discussing alternating currents and voltages because AC ammeters and voltmeters are designed to read RMS values, and many of the equations that will be used have the same form as their DC counterparts, so it's convenient. And wherever you take a meter reading on AC, if they tell you it's read with a meter, it's RMS, so be very careful with that. It's not going to be peak, but you have a relationship between RMS and peak. It just involves the square root of 2. Okay, so the average power delivered by a source is converted into internal energy in the resistor. The resistor is the only power dissipating part of a series RLC circuit. There are no power losses with pure capacitors or pure inductors in an AC circuit. In a capacitor, during one half of the cycle, energy is stored. During the other half of the cycle, the energy is returned to the circuit and no power losses occur in the capacitor. In an inductor, the source does work against the back EMF of the inductor, and the energy is stored in the inductor. But when the current begins to decrease in the circuit, the energy gets returned to the circuit. So the only place where energy is used in an AC circuit is in the resistor, and that's a good thing. Okay, because the resistor doesn't care which way the current is flowing. So its only job is to turn electrical energy into thermal energy. So the power delivered by an AC circuit depends upon the phase, and that's this right here. So power equals ERMS, IRMS times this cosine phi, and here's the phi as the phase. Some applications include using capacitors to shift the phase to heavy motors or other inductive loads so that excessively high voltages are not needed. Power is maximized if the current is brought into resonance. In other words, XL equals XC, or omega equals omega D. Now, a homework note, be careful with power factors. The cosine of phi is the cosine of minus phi. So the power factor cosine phi cannot be used to determine the sign of the phase or if the circuit is inductive or capacitive. By the way, here's a resonance curve. We're going to talk more about this later. We have a much more detailed one on the next couple slides. Okay, so power factor and resonance. Remember that cosine phi is cosine minus phi, so you cannot determine whether the circuit is inductive or capacitive from the power factor alone. When cosine phi equals 1, you have resonance. This maximizes the power, which is usually a desirable thing. Now, if you think of an electrical grid, most large loads in a typical power grid are inductive. Motors and transformers are everywhere in a typical power grid. Power companies place capacitors throughout their distribution system to counteract the inductance and get the power factor as close to unity as possible. When cosine phi equals 0, you have either a purely inductive or purely capacitive load, and the power equals 0. This is just like having an open circuit and is very undesirable. The power company wants to sell you energy. Energy is power times time. If they have cosine phi equal to 0, they're not selling you energy. Now, resonance is used also for tuning out undesirable frequencies of electromagnetic radiation in favor of a narrow band of desirable ones. This is how TV and radio tuners work. It's also used in EM filters too. We'll also talk about LC circuits, and that'll be for some other topic, one of the other lectures. That is for the Physics 222 students, not the Physics 122 students. So power can be expressed as a function of frequency in an RLC circuit. And we can rewrite that as power equals ERMS squared times R times omega squared divided by this factor, R squared omega squared plus L squared times omega squared minus omega D squared. This shows in a resonance where omega equals omega D, the average power is maximum because this term goes away. So at resonance, you wind up with a power equals ERMS squared times R times omega squared divided by R squared omega squared. And of course, this is 0. One of these, of course, omega squared cancels out, and we lose one of the R's. So then we wind up with power as ERMS squared divided by R. Now, most large loads, motors and transformers are inductors. Power companies place capacitors in their distribution system for maximum power transmission. You want resonance. And power companies are always trying to achieve resonance. Okay, so here's that resonance curve I talked about before. Now, you might want to copy this into your notes because this is rather handy. It's a plot of the amplitude of the current versus the frequency. And they wrote the frequency in terms of omega D divided by omega. Omega D is, of course, what the generator drives it at. Omega is the natural frequency of the circuit. Now, at this point, omega D and omega are equal to each other, and that, of course, is omega D or omega equals 1. On the left is the low frequency side, and, of course, remember the XC is 1 over omega DC. Now, in low frequency, omega D is small, so XC is large. That means XC is large compared to XL, because XL is omega D times L. So XL is small at low frequency. So we call this a capacitive circuit. That is, XC is high. Capacitance is low, the inductance is low, and F and omega are low. So this is the low frequency end. If you take this all the way to 0, so in other words, the frequency is 0, that's DC. XC has a tendency toward infinity. You can see that if you plug 0 in here, this is going to go to infinity. So XC gets extremely high. The capacitor acts like an open circuit. So in other words, the power goes to 0. XL also goes to 0, so the inductor acts like a short circuit. Now, at the high frequency end, which is this side, this is the inductive side because XL is greater than XC. You can see that. This is high. And, of course, this one will wind up low. So XL is high, the capacitance is high, the inductance is high, and F and omega are high. And XL is greater than XC. And as you take this to extreme, as the frequency gets extremely high, goes to infinity, XL will also go to infinity, and you can see that by looking right here. And if the frequency goes to infinity, XC also goes towards 0. So at this end, the inductor acts like an open circuit, capacitor acts like a short circuit. Either of these extremes is undesirable when it comes to a power grid or to transmitting power with high efficiency. So power companies want this. Now, if you look at these curves, you see these different curves. These are for different resistances. At resonance, the current in the circuit depends upon the EMF and the resistance. As the resistance drops, the current gets higher because V equals IR. So at resonance, omega equals omega D, and of course, the formula for that is 1 over the square root of LC. XL would equal XC, so VL equals VC. But they're out of 180 degrees out of phase with each other. So when one is high, they just slosh back and forth. The energy slosh back and forth. Phi equals 0, so cosine phi equals 1, and that makes the power factor 1. So the power is maximum. Power is just IRMS, ERMS, so it looks like DC. And that is IRMS squared times R, or ERMS squared divided by R. The power is at a maximum. VR and IRMS are at maximums, and VR equals IRMS times R. The circuit acts like it only contains a pure resistance. And to a power company, that's great. Okay, so here's an example. We have a driven RLC circuit. We want to calculate the power factor and average factor. A series RLC circuit is driven with an ERMS of 120 volts at a frequency of 60 hertz. It contains a resistance of 200 ohms, an inductance with an inductive reactance of 80 ohms, a capacitance with a capacitive reactance of 150 ohms. What are the power factor, cosine phi, and the phase constant phi, and the RMS current of the circuit? What is the average rate P at which the energy is dissipated in the resistance? And if we wanted to bring this to resonance, that is to maximize the power, what new capacitance would we need? We can't change anything else. Okay, the physics of this is a series RLC AC circuit. And the first thing I look at here, I see XC is greater than XL. So I know I'm in the capacitive side of the resonance curve. So I'm below resonance. So we write down our knowns and unknowns. Resistance is 200 ohms, XL is 80 ohms, XC is 150 ohms. The RMS value of E is 120 volts. Driving frequency, which is the generator frequency that will rule the circuit, is 60 hertz. We want to know the IRMS, the phi, and whatever new capacitance we need to get the power to maximum. In other words, we want to achieve resonance. The formulas for this are cosine phi equals R over Z. Z is just the square root of the sum of R squared plus this quantity XL minus XC squared. P is then IRMS divided by R. IRMS is just ERMS over Z. XC equals 1 over omega DC, and omega D is just 2 pi FD. At this point, we start putting things together. The cosine of phi is R over Z. We plug in for Z, and we find that cosine of phi, which is the power factor, R divided by the square root of R squared plus XL minus XC squared. Okay, we plug in our numbers. Cosine phi will equal this R of 200 ohms divided by the square root of this R squared, which is 200 ohms squared, plus square of 80 ohms minus 150 ohms. That's XL minus XC. When you do the numbers, it ends up 0.944. It's close to resonance, but not quite. If we take the inverse cosine of that, we can say that phi is either plus or minus 19.3 degrees. Now, we just determined by looking at the resonance curve and by looking at the fact that XC is greater than XL, the circuit is mostly capacitive, so current leads EMF and phi is less than 0. So phi is a negative 19.3 degrees. So P is IRMS squared times R, and of course IRMS is just ERMS over Z, so P equals ERMS over Z, that quantity squared times R. And we can rewrite this as ERMS squared times R divided by the quantity R squared plus the square of XL minus XC. We're ready to plug in numbers. We have our 120 volts for ERMS. We're going to square that. A resistance of 200 ohms. We have a resistance of 200 ohms. We're going to square that. And we have an XL of 80 and an XC of 150. We're going to square the difference between these two. When you do that, you wind up with 64.1 watts. IRMS is just the square root of P over R, or the square root of 61.4 watts divided by 200 ohms, or 0.554 amps. So 64 watts at 554 milliamps. Now, we want to get resonance. We want phi equal to 0, XC equals XL. And of course, XL is 80 ohms. We're not allowed to change L or anything else. The only thing we can change is C. So we would need to set XC to 80 ohms. XC is 1 over omega DC. So we're going to solve this for the capacitance. The new capacitance will be 1 over 2 pi times 60 hertz times 80 ohms. Just turning this around and substituting 2 pi f for omega d. So new capacitance is 3.32 times 10 minus 5 farads, and the old capacitance is the same thing, only using this old XC that we had before. It ends up being 1.77 times 10 minus 5 farads. Now we need a larger capacitance, which is good because it's easy to do that. You either replace the old capacitor with a new one, or even better than that, you just connect an appropriate one in parallel. So you subtract these two to find out what you need to add to this one, and you put that across this one in parallel to get that. Which one of the following choices will reduce the amplitude in an LRC series AC circuit? Well, you don't know anything here. You don't know whether this is above or below resonance. So the only thing you can do is increase the circuit resistance. Okay, so you need to increase the impedance Z, since we do not know if this circuit's at resonance at or above or below. We can't be sure of how to change the capacitance or inductance to reduce the impedance. A capacitor connected to an alternating current power supply. Assume there's no inductance or resistance in the circuit. The capacitor is replaced with another that has a larger capacitance. What is the effect on the RMS current in the circuit and the capacitive reactance? Okay, the RMS current is going to increase because remember, IRMS is VRMS divided by XC. And of course, XC is 1 over omega DC. So when you substitute in for this, IRMS is V times omega DC. So IRMS is proportional to C. 5 identical capacitors are connected in 3 different circuits as shown. The AC current source in each circuit is the same. In which circuit is the RMS current the largest and which is the RMS current the smallest? Well, this is a little related to this one. You look back here, IRMS is proportional to C. The one that's going to be the largest is going to be the one with the capacitors in parallel. So this one's going to be the largest one. This one will be intermediate, and this one will be the smallest one because capacitors in series go as 1 over. C has the largest RMS current and B has the smallest. IRMS is V times omega D times C. So parallel has the largest C equivalent and series has the smallest. So circuit C will be greater than circuit A and then will be greater than circuit B. 4 circuits are set up so that each contains an AC source and an inductor. Circuit A has a 50 hertz source and a 15 millihenry inductor. Circuit B has a 60 hertz source and a 10 millihenry inductor. Circuit C has a 100 hertz source and a 2 millihenry inductor. And circuit D has a 50 hertz source and a 4 millihenry inductor. Rank the inductive reactance for these circuits in orders from largest to smallest. So what I do with something like this is eliminate stuff I don't need to know and make a table. So XL equals 2 pi FL. First thing I see is this 2 pi. It's the same for all of them. So XL is proportional to FL. Now the next thing I need to do is to check units. They're all in millihenries and hertz. So this means I don't have to multiply by 10 to the minus 6. I make a table out of this. Frequency in hertz, inductance in millihenries. And I multiply the frequency times the inductance and find out what the numbers are. And they want the largest to smallest. Okay, the biggest one is A, then B, then C and D are equal to each other. So A is greater than B, greater than C, and equal D. An inductive circuit operates at a frequency of 120 hertz. The peak voltage is 120 volts. And the peak current through the inductor is 2 amps. What's the inductance of the inductor in the circuit? It ends up being 0.08 henries or 80 millihenries. Now, both I and V are peak values. And we can use this with peak values. It's okay to use V equals IXL for this. So V equals I times XL, and that equals 2 pi F times L, and that's just substituting XL. And L will be V divided by 2 pi F I. So 120 volts divided by 2 pi times 120 hertz times 2 amps. It ends up being 0.080 henries. Now you have to be careful with this, okay? You can use this as long as they're both peak or they're both RMS. Don't use it for instantaneous. Okay, the graph shows the current as a function of time for an electrical device plugged into an outlet with an RMS value of 120 volts. What's the resistance of the device? So I'm going to look at the peak values. The peak current is 10 amps. The RMS voltage, 120 volts, is a peak of 1.41. That's the square root of 2 times the RMS value of 120 volts, 170 volts. V equals IR, so R equals going to be V over I, and that's 170 volts divided by 10 amps. So that's a 17 ohms. A circuit contains an AC voltage source, a resistor, and another component. The voltage amplitude is held constant as the frequency is increased. The current in the circuit is observed to increase as the frequency is increased. What is the additional components in the circuit? Well, it's a capacitor. Capacitors act like an open switch at low frequency and like a short at high frequency. As the frequency increases, their reactance decreases. That means the impedance of the circuit also decreases, and that means the current increases. If this was a resistor or an incandescent light bulb, there'd be absolutely no effect, so we can eliminate that. If there was an inductor, the current would decrease as the frequency increased. Inductors act like an open circuit at high frequency. The circuit contains an inductor, a light bulb, and a source connected as shown. In which frequency limit is the light bulb the brightest? Well, I remember that the reactance of a capacitor goes down as the frequency goes up. If the reactance goes down, it acts like a wire to the light bulb. Okay, so this means the light bulb will be bright at high frequency. If you look at the inductor hates high frequency, so its reactance is going to be extremely high. So it's like this is a huge resistance and that's a wire. So the light bulb is going to be brightest at the high frequency limit. Capacitor acts like a short at high frequency. The inductor acts like an open. The most current will flow through the capacitor and the bulb at the high frequencies. A resistor and inductor and capacitor connect in a series with a voltage source V equals V naught times the sine of 2 pi ft. Which one of the following statements concerning this circuit is false? The one that's false, it says the impedance of the circuit is equal to the square root of XL squared minus XC squared. The correct formula is Z equals the square root of R squared plus XL minus XC quantity squared. Okay, let's go back for a minute and examine each of these choices. Okay, this one says the current through each of the circuit elements must be the same. Well, it's a series circuit. So yes, the current through each of the circuit elements must be the same. So that one's true. The next one says the sum of the instantaneous potential differences at any time t across each of the elements must be equal to V equals V naught times the sine of 2 pi ft. That one's true also. Third one says the current through at least one of the elements is equal to I of t equals V naught over Z times the sine of 2 pi ft minus V. That one's true. Now this one we already identified as being false. The voltage of one of the elements has a different phase angle than that of the other two elements. That's also true. So the only one that's false is this. I also included this handy summary of the peak and RMS formulas and when and which to use. Here are the circuit elements: resistor, capacitor, and inductor. Here, of course, is the average power in terms of watts. And of course, for the resistor, VR equals E max squared over 2R, or VRMS squared over R. Capacitor, average power is 0 in a capacitor, and inductor, it's also 0. The reactance is in ohms here. Of course, reactance of resistor is just the resistance. And then for the capacitor, XC equals 1 over omega C, or XC equals 1 over 2 pi FC. For the inductor, XL equals omega L, or XL equals 2 pi FL. The phase of the current here is for the resistor, the current is in phase, and phi equals 0. For the capacitor, current leads the voltage by a quarter of a period, and phi will then be equal minus 90. And for the inductor, the current lags the voltage by a quarter of a period, and then phi would be positive 90. The voltage amplitude, of course, the units on this are volts. VR for the max is I max times R. VR for the RMS is I RMS times R. Of course, resistor doesn't make any difference. Okay, for the capacitor, VC max equals I max times XC, and VC RMS is I RMS times XC. For the inductor, VL max equals I max times XL. VL RMS equals I RMS times XL. Now, be careful with these right here. Use the voltage equations only for the amplitude or peak values or for the RMS values. Do not use these for the instantaneous ones. They won't hold for instantaneous. Thank you.